everybody, and welcome to the IFT 372 online study session. As per usual, some of you are regulars at this point. I don't have specific plans to discuss on these sessions, but generally what we look at is homework, activities, things with priority first, and then we can go back and look at things like the study guides for the practice final and other things like that. But typically we start with issues that are of more priority, I guess you could say, for most people. But again, we start with, this is an opportunity for you to have your questions answered. So if you have any questions and we're sitting around waiting for people to propose something and nobody said anything, then feel free to ask any sort of question you have and we'll see if we can't make it a little clearer. So again, we'll give it a couple minutes here just for people to attend. So for this week, for week 7, we have a couple things going on. We have the homework, we have the activity, and then the extra credit assignment. Just up front, for the extra credit, because it is extra credit, I'm more than happy to give you kind of an outline or clarify what some of the questions are talking about. I'm not going to go through as much specific detail or necessarily walk through all the questions for the extra credit, because it is just that, it's extra credit. But if you have a question and you don't understand what it's asking you or something like that, then I'll definitely clarify that. But I'm not going to go through and give a step-by-step breakdown like I would for a homework question. And again, the extra credit is entirely optional, so if you don't need to or feel like doing it, you don't necessarily have to. We'll give it a couple more minutes here. We'll go till 5 after, and then we'll get started running. So you may or may not be the only one at the beginning, but that's happened before and it hasn't stopped me before. So alright, a couple more of this, Spencer. And just from looking at the homework, it looks like a good portion of the questions are kind of definition questions. So I'll try to, obviously those don't require as much explanation because they are mostly based out of book reading. But let me see here. We'll cover whatever we need to cover. So the math ones are obviously the easier ones to explain because there's a math problem there, and I can explain the subcategories of it. The definitions are kind of hard to talk about without just giving the answer straight up. But if you do have a question on one of those, I'll do my best. Alright, it's 5 after. Let's go ahead. So if you guys, either of you two, have any questions, let's go ahead and get started. Okay, so Ryan's got a couple. I had a question about the formula for 11.2. I found one that seems to fit, but I'm not sure. Okay, let's take a look. Let me just pull up the proper text for 11.2. And then if you want to also post the formula that you have, we can do a comparison and see.
Data rate equals number of data subcarriers times number of spectral streams times data bits per subcarrier
divided by time per OFDM symbol in seconds. Okay, so that's the formula you're looking at there. And that looks...
number of data subcarriers.
Yeah, that looks to be about the formula that I'm seeing here. And so let's just get the rest of the question. Just write the rest of the question out so we have all the variables before we start tackling it. For 11.2, so we're asked to determine the data rate. So data rate equals question mark. That's what we're trying to find for 16 QAM, with a 2/3 coding rate, with 2 parallel data streams. And then part A is asking us for a 20 megahertz channel. So those are the variables summed up from what we've started with. And so for the math, we're going to be using basically what Ryan's formula was. So let me write that out. Grab it here. Okay. And so, for the number of data subcarriers, let's see. Okay. So this is the tricky part, is basically taking what Ryan said with his formula there and then transferring the data that the numbers that we have into that formula. And so if we, let me just pull up some other information real quick, just a second, sorry. Basically, the first thing we need to find out is the number of data subcarriers, because we're not told that explicitly in the problem. We're told that we're using 16 QAM, we're using two parallel streams, and a 20 megahertz channel. And so we need to figure out the number of data streams we're talking about, or the number of subcarriers, sorry. So, oh, hang on. I'm trying to see if there's an easy explanation for some of these numbers. Sorry, I'm just looking up because I can just give you the numbers, but that's not going to help anybody. So I'm trying to make sure I can explain. Okay, so if we go back and look at, so this is just straight out of the book, and that's the best explanation I can give. On page 351, when it's talking about the channel structure of 802.11, it specifically says that figure 11.14 shows the channel structure used by 802.11a and also by 802.11n, and that's what we're concerned with. Because if we go back to the problem, it's asking us for 802.11n implementation. And so, based on that, further down in that section, we see that, where are we? The system uses up to 48 subcarriers. So given that we have 48 subcarriers, that's the first information that we can plug in here. So we'll have data rate equals, and so we have 48 subcarriers per 20 megahertz. Or we can just write 48 subcarriers, because that's what we're given for this channel. Our single channel of 20 megahertz has 48 subcarriers. And then, to finish off or not finish, but continue with Ryan's formula, we have the number of spectral streams, and we've been given that there are 2 parallel streams. So we have 2 streams. And now we have to look at the data bits per subcarrier. And again, this is going to make me look. Okay, so this one's actually not too tricky. So, data bits per subcarrier. Now remember that we're using 16 QAM modulation for this problem. It was specified in the beginning that we're using 16 QAM. So if we're using 16 QAM, how much or how many bits are we using per symbol for a 16 QAM system? And Ryan says 4 bits. Yep, that's right. So for 16 QAM, we're using 4 bits. Hello, Stephen. Glad to see you can join us. But it is actually 4 bits. And we find that by, remember that we have log 2 of m, or our modulation level, equals number of bits. And so in this case, we have log 2 of 16, because we're using 16 QAM. And that gives us 4. So it's not just looking at the number of levels we're using, we have to figure out how many bits we need for the number of levels. And so we've determined that we're using 4 bits per symbol because we're using 16 QAM, but we have a 2/3 coding rate that we need to keep in mind. And so in case you're wondering what the coding rate is, it's basically saying that 2/3 of the bits that we send are actually used for data. We're using 1/3 of the bits for other, basically meta information like error correction. Error correction is the typical one. So 1/3 of the bits that we're using are not actually data bits, they're error correction. And so that means for actual data bits per subcarrier, we have 2/3 times 4. And let me put that in parentheses. Because again, we're using 4 data bits basically per symbol because we're using 16 QAM. But then we have a 2/3 coding rate, which means that only 2/3 of all the bits that we send are actually data. The other third are being used for non-data purposes, such as error correction. And so this is addressing our data bits per subcarrier section. Right here. And then lastly, we have the last bit of our formula, which is time per OFDM symbol in seconds. And so for this one, let me see. This might take me a second again to get the proper explanation. So apologies. While I'm looking for this next section, if anybody else has a question based on what we just did, feel free to ask it, and I'll keep... Again, I'm just trying to make sure that I don't just give numbers out, because that's easy to do. But I'm also trying to see if it's clearer in the lecture material. Let me see. Okay. Yeah, so that you see the numbers I'm getting here are different from what I'm have in my notes, so it's a bit tricky, but so generally what I think I'm just going to have to sum up this one. But basically what it's asking is it's the time per OFDM symbol. So typically what we would look at for this is, again, if we look at page 3, which page was it? 352, it states that when we're talking about subcarrier frequency for OFDM, or specifically for 802.11a and n, each subcarrier transmits at a rate of 250 kilobaud. So 250 kilobaud. Now again, this is not kilobits per second or anything like that. This is kilobaud, which means 1,000 symbols per second. So it's broadcasting 250,000 symbols per second. And so if we're trying to find the time between OFDM symbols, then we would take the inverse of this. And again, that gives me a number that is slightly different than the intended value. So I'm trying to figure out, because if we do that number, that gives us 4 times 10 to the -6th. That's not the number that is in my notes here. So I'm trying to figure out the discrepancy there. That would be the general thought process if you were trying to find the time per OFDM symbol. Because again, the symbol instantaneously, for our purposes, instantaneously happens. And then, because we're transmitting at this rate, the inverse of that means that we have 4 times 10 to the -6 seconds between each symbol. Because you can have a symbol instant wait, 4 times 10 to the -6 seconds symbol, and that'll give us a total of 250,000 a second. Now again, this is not quite the number I should be getting, so I'm trying to figure out where I'm making my mistake. Confirming it is kilobaud, yeah, so it's 1,000 baud, not just regular baud. But still the question remains as to why this is not the correct number. Let me look in some of the lecture materials and see what we have. Actually, I value your guys' time, so I'm just going to plug in the number that I'm given here, which is 3.7 times 10 to the -6. And so that's the number that I'm trying to figure out, is why it would be 3.7 instead of 4, because the way I'm seeing it, it's 4. Let me see. But for the sake of not taking up the full hour on this one problem, I think I'm just going to move forward. So, and again, I apologize for having to do that, but I don't want to waste the whole time on this particular problem, because there are more problems to be had. And so, now that we have these numbers put together, we can calculate out our data rate. And then I'm just doing the math right now. Oops, sorry, that is not a 3.7, that's a 3.6. My apologies. And so with this number, with these numbers rather, I got an answer of 71.1 megabits per second, or technically I got 71.111. Actually, that's sufficient for explanation purposes. Now that's me doing the conversion there. By default, I got 7 1.11 bits per second. But I just did the conversion to the larger unit. And so again, I think these first three are clear, right? We determined that there's 48 subcarriers from the book, which told us on page 351 that the system uses up to 48 subcarriers. And so based on what the book was telling us, that in our channel we have 48 subcarriers. And again, that's just from the book saying that's what 802.11a and n also make use of, are 48 up to 48 subcarriers. Times 2 streams, and we were told from the beginning that we had 2 parallel streams. And then for data bits per subcarrier, we remember that we have 4 bits per symbol because we're using 16 QAM, which means that we're using 4 bits because we need 4 bits to represent up to 16. 0 to 15 in binary requires 4 bits. But we have a 2/3 coding rate, which means that only 2/3 of these 4 bits are being used for data. The other third are being used for meta information like error correction. So only 2/3 of the 4 are actually data bits per subcarrier. And then the time per OFDM symbol is 3.6 times 10 to the -6. That's what we're using for this. Again, I have to do a little bit more research as to why it's specifically 3.6, because my quick calculation would put it at 4. But for the purposes of this problem, we're using the value of 3.6. And that, if we multiply it out based on Ryan's formula, we end up with 71 million bits per second, 71,111,000, which will round off to 71.1 megabits per second. Is that 3.6 times 10 to the -6 a constant for 802.11n systems? Ryan, that's a good question, and it might be. Are you seeing that somewhere that makes you think that it is? Because I'm looking through some of the lecture material and I'm not seeing that immediately, but that would be a good explanation of why that's the case. Page 358. Oh, that would be lovely if that's where that is, because that would make so much more sense. 358. Oh, would you look at that? Thank you, Ryan. So yeah, that looks like that is the constant that they're using. So like he said, on page 358, we have the example formula, which is probably where Ryan pulled his formula from as well. But he has the valuation where they say that the time per OFDM symbol is 3.6. And so that's likely what they're using as a constant for 802.11n transmissions. And so, but the assumption that we can just jump to double the numbers is not quite right. Let me explain to you why that is not right. Because that would be the safe assumption to think, is that you could just double, because we have double the channel width, we can fit in twice as many subcarriers, but we can actually fit in slightly more. And the reason we can do that see. If you look at the equation, like what you pointed out on 358, thank you for pointing that out, by the way. For 802.11n, they're using 104 as the number, 108 as the number of data subcarriers. And so that's what we can use instead when we're using the full 40 megahertz, is we want to use the value of 108, not 96, which would just be double it. And now let me see where in the book it explains that, because I'm sure it does somewhere. Brian is just better at finding these pages than I am. Oh, Ryan, yes, you are on it. Thank you. I'll blame it on the fact that I'm juggling a couple different plates. But yes, Ryan absolutely has it. So on page 355, looking at the, like he said, the end of the first paragraph, the effect is that 802.11n achieves slightly more than double the rate with 40 megahertz channels. So again, we saw that they use 48 subcarriers per 20 megahertz, but if you use 802.11n, you can use 108 per 40 megahertz. 8 channels per 40 megahertz, 48 channels per 20 megahertz. And so that's an important distinction to make, is just because our channel is twice as large, let me actually make this clear, this is for part A. Just because our channel is twice as large does not mean we just have twice as many subcarriers. Because of the extra space and the changes we make with that space, we can actually be slightly more efficient with our use of the channel. And so for part B, again, pulling from the formula, data rate equals 108 subcarriers. Oh, that needs to be bigger. Times, and part B has different requirements, so let's make sure we've got the right requirements. Everything's the same except for the channel. Okay, so that makes it easy. So again, we have 2 streams times a 2/3 coding rate times 4 divided by our constant, or the number that they're telling us we need to use for this. I'm not comfortable completely calling it a constant, but it is, at least for our purposes, we're using it as a constant. And so that equals, and if we calculate it out, 108 times 2 times, and be careful with your parentheses or you'll get something different. And doing it like this, we get 160. I'll just write out the full number first. 123 bits per second, or in reasonable terms, 160 megabits per second. And so again, thanks to Ryan's sharp eyes and more efficient book hunting than I, we've found our answer. So again, just to break down what we did here, our conditions don't really change except for the size of the channel. So let me just make that clear. Everything else is the same. And so when we look at our data rate formula, which is data rate is number of subcarriers times number of spectral streams times data bits per subcarrier, all of that divided by the time per OFDM symbol. And so looking at our numbers here is that we're given that our data rate, we're given that 802.11n has 48 subcarriers in a 20 megahertz channel. And that's listed on, let's see. The easiest way to see that is outlined on page 355. 355, which states that 802.11a and G use 48 subcarriers per 20 megahertz, which is what 802.11n is. We consider them the same in 20 megahertz channel. So 802.11n equals 48 subcarriers per 20 hertz, subcarriers per 20 megahertz, that is. But then, if we're increasing that size, we have 108 subcarriers per 40 megahertz. The increased size, like the book goes into explain a little bit, with the increased size lets us work with slightly more than double. So it's slightly more efficient if we use double the space. Those are where those numbers are coming from. And a lot of this is basically just look at the book and use the numbers it gives you and explains, because going into the details of why this works is beyond the scope of the class. You're getting into a little too much, a little more than you need to know. And so that's what we're basically looking at for 11.2 after all this time. We split it down. We're using this base formula, and then we had to find out some of these numbers. We had to find out the subcarriers from the book. We just had to make sure we were reading the right section. Number of streams were given. Coding rate was given, but we had to figure out what that meant in effect for the data bits. Because again, we're using 4 bits in a 16 QAM system, but 2/3 of those are data bits. The other third is our metadata, such as error correction, and then our time per OFDM symbol, which was given in the book. So it's basically just a case of figuring out what numbers you need to plug in to the formula. But it took a lot of time to do that, so let me go back and make sure I'm familiar with 16.7. So Ryan, the next question you said was 16.7. Did you have anything in particular that was confusing you about that one? And we'll probably, I don't know if everybody can stay, but we'll extend this a little bit longer because that took longer than it should. Was 16.7 just getting started? Because it looks like it might just be getting started with it. Oh, okay. Well, it looks like Al is having issues with this one, so let's address this one. And the only reason I want to focus on the math ones today is that we still have a little bit of time between now and Sunday for you to look at some of the book ones. But if we can get the math ones out of the way, then you can spend some more time looking at the ones that just require what I was just doing. What Ryan was helping me with there is just looking through the book and getting definitions or answers. Okay, so for part A, the question is asked for 16.7. We're told that we have a TDMA network and we have 5 stations sharing a single transponder equally. The frame duration is 2 milliseconds. Preamble time per station is 20 picoseconds. I'll just do a U. Hopefully that's sufficient. we have guard bands of 5 picoseconds. And that's used between each burst. And then the bursts equal QPSK at 30 megabaud. And remember, that's megabaud, that's not megabits. So that's saying that there's 30 million symbols per second, which may consist of multiple bits. And they in fact do if we're talking about QPSK. So just something to keep in mind. You may have, I think some of the earlier problems or homeworks have addressed the issues of baud, but they did not necessarily fully address. Oops, hold on. You didn't necessarily have to use them practically yet. There we go, everything's better. Okay. So part A is asking us to calculate the number of 64 kilobits per second voice channels that each TDMA earth station can transmit. So for part A, we're asked to find the number of 64 kilobits per second. And again, now we're down to bits per second, not baud, that each station can support or transmit. I'll use the exact terms. And so we kind of have to approach this in a bit of a roundabout way. And the first thing we need to do is we need to figure out the amount of time, because again, what we're talking about here is this whole chapter 16 is talking about satellite and long-range communications. And so that means when we have these ground stations, we can't all be broadcasting at the exact same time to the satellite. We need to take turns. And so generally what we want to start out with is trying to find the amount of time that's available for each station to burst. So we need to figure out, okay, we have X amount of stations, how long can each of them talk before the other one has to take its turn? And we can do that by using, and let me see if this formula is listed elsewhere, but basically if we're just trying to take the amount of time that each station can burst, we have burst time is equal to the frame time, because that's, or frame duration. But then within that frame duration, I'll shorten that to frame D because that makes it a bit easier. Within that frame duration, we have a preamble and guard bands that are not what we generally want to, they're not part of our information. Right, they're additional meta information that doesn't actually contain the data we want. The preamble is giving particular information, and the guard bands are just little spaces in between to say, okay, this is the end of one transmission and the start of another. Ignore the guard band, you know to switch over. And each of those preambles and guard bands occur per station, because obviously here we have preamble per station, that was defined. But then a guard band, the purpose of the guard band is that, like it says in this question, guard bands are used between bursts. So between every burst, there's a guard band. So that means we have the number of stations. For each station, there's a guard band plus the preamble time. And so that is subtracted from our total frame duration, because each frame consists of 2 milliseconds. But then within that frame, we have split up. We have to basically split that total frame time between each of the stations that need to broadcast. And with each station that we're adding, we have an additional preamble and guard band we have to account for. And so if this is our total time, that's our total time available, we need to then divide that by the number of stations. And that will tell us how much time each individual station has to broadcast in a burst. Because again, we have the total frame duration minus guard times and preamble times for each individual station, because again, we'll have a preamble for each station, we'll have a guard time for each station. And by doing this subtraction, we're telling the amount of time that's actually available for data transmission. Because all this time here, the number station times guard time plus preamble time, that's not data time. We're not using that time for data transmission. We have to use that for either guarding or adding the preamble information we need, but it doesn't actually contain the data we need. So when we subtract that out from the total frame time and divide it by the number of stations, we find the amount of time that each station can actually use for data. And so if we plug in these numbers here, we have 2, and again, I'll just do the conversion to, let's see. So again, we'll just convert down to picoseconds because that's what the smallest unit we're dealing with, or the base unit. You could do it, as long as you're consistent with your units, it doesn't really matter. But since the majority of our units are already in picoseconds, I'm going to keep it that way. Let me just make sure we're all on the same page, okay? And so we have 2,000, because remember, 2 milliseconds converted down to picoseconds, we have to do that conversion. Minus 5, which is our number of stations. We have 5 stations. That was given in the original problem. And then our guard time is 5 picoseconds. And remember, we have a guard time for every station because we have to separate our bursts. Plus preamble time, which was 20 per station. And then again, we divide that quantity by the number of stations. And so our burst time ends up being 375 picoseconds. And again, those units could be whatever you want. I just decided to do it to picoseconds because 2 of our 3 values that we were given were already in that unit. And so instead of having to convert everything, I just had to convert the 1 extra one. But this doesn't quite give us the answer we're looking for, because we're being asked to find the number of voice channels that each T2MA station can transmit. And that's not what we found. We just found the amount of time that's available for them to communicate. And so how do we get from the next step? So we know that we have a transmission rate. Our bursts are transmitting at 30 million baud. And so that's 30 million symbols per second. And so what we're given here is that we're transmitting, we have a burst time of 375 picoseconds. Now, here's a question, and again, this is similar to what we did for the last question. We're talking about symbols here. We're not talking about a bit rate. So again, this is symbols per second because it's millibaud. We're not talking about a bit rate yet. But we're told that we're using QPSK as our modulation scheme. So can somebody tell me, again, can somebody tell me how many bits are needed for a QPSK modulation scheme? So again, we're using QPSK as our modulation scheme. So we have log, and again, to solve this, we have log 2 of m equals the number of bits. And it might help you if I say that QPSK is short for quadrature phase shift keying. Quadrature. And Ryan says, yep, log 2 of 4 equals 2, because a quadrature phase shift keying uses 4 encoding levels. So our m value is 4. Log 2 of 4 equals 2. Al says his notes are wonky. That's fair. That's an excuse I'll accept. And so now that we have that, we know that our bursts, instead of saying that they're 30 millibaud, we can now say that because each symbol is represented by 2 bits, and we're broadcasting 30 million symbols a second, we can say that's equivalent to, so again, each symbol consists of 2 bits, and we're multiplying it by 30 million symbols per second. So that means each second we're transmitting 60 million bits. So our bit rate is 60 million or megabits per second. And so that gives us a data rate, which is a little bit more useful. But now we're still not quite done, because we know that we're transmitting, every burst that we have is transmitting at 60 megabits per second. That's great. We have a burst time, which means we know how long the burst time is. But what we don't quite know is basically the capacity of each Earth station. And let me pull up my notes here. Where are we? Let me see if I can explain that in a different way. So if we look in the book, and again, this is going to be referring back to the book because that's a lot of what this homework is. I'm just trying to find a more succinct explanation of this formula. Anyway, what we need to know now, we have a couple different bits of information, but we now need to bring it all together. And so each Earth station, we basically just have to look at the number of bits we transmit in a burst, so hang on, let me just do some quick math here. So what we have is, at this point, we have a bit rate of 60 megabits per second. So we know that that's the rate that we're transmitting at. We know that each burst happens over the course of 375 picoseconds. And so one of the things we can figure out that we have Oh, sorry, I keep calling these picoseconds. I've made that mistake before. Those are not picoseconds. Those are microseconds. So, if any of you are sharp on your metrics, yeah, these are microseconds, not picoseconds. Apologies for that. If you've been doing your math with picoseconds, you've been off significantly. But anyway, so we have 375 times 10 to the negative 6, because that's what a microsecond is, times 60 million. Now the problem we have here is that this is 60 million bits per second. right? And so this comparison doesn't quite work because we are not using a full second. Although I think with these units it actually works out all right. Yeah, actually, never mind. If you write it out this way, it works fine. You just can't. Make sure you're including the 10 - 6. And so this is the, and again, this is for station capacity. Because now we're actually trying to find the bit rate or how much data these stations can push. Ryan says, yes, I was wondering. Yeah, my apologies. All of us get rusty on our metric units from time to time. And so now that we have, again, just to walk it back to why we're doing this calculation, we have the amount of time that each individual burst lasts, right? And we calculated that into 375 microseconds. And that was based on our calculation up here. And then we also found the data rate that those bursts occur at, which was 60 megabits per second. So that's the rate that we're transmitting at, and this is the amount of time that we're transmitting at. And so this will tell us what the amount of data we can push is. But we are limited. This formula isn't quite complete yet because we're limited to the fact that our frame duration is only so long. Our frame duration is only 2 milliseconds. And so if we have to divide by the frame time, and my units, this is going to get a little bit messy here, but this is basically telling us divided by 2. And so by doing these numbers out like this, we're telling us ourselves that our data rate, or our capacity rather, not our data rate anymore, the amount of data these stations will transmit per burst is 11.25 megabits per second. Because again, we have the amount of time that a burst occurs, 375 microseconds. We have the data rate that we're transmitting during that burst, which is 60 megabits per second. But then we're limited by our frame time, which is 2 milliseconds, or basically a 2,000th of a second. And that tells us here that our data rate, or no, again, I keep saying data rate, that's not right. The amount of data we transmit in one burst per station is 11.25 megabits per second. Or just megabits. That's our capacity of our station. So let me actually replace SC with something a little clearer. And now this is the amount of data that our station can support. And we've calculated that out. That's how much data our station supports. But now we're getting to the actual question, which is, we have this amount of data. We need to split that into 64 kilobits per second channels. And so how would we do that? If we have a total amount of data, which we calculated here, so each station gets out 11.25 megabits per second, and we need to fit in 64 kilobits per second channels, what's the easiest way to break that down? Or solve that number, I guess, would be the correct way of saying it. How can we figure out how many individual channels of 64 kilobits per second we can support with a total capacity of 11.25 megabits per second? Ryan says 11.25 times 10 to the 6th divided by 64 times 10 to the 3rd. And so his extra units there, the 10 to the 6th and 10 to the 3rd, are converting our mega and kilobits, right? So what he's doing is he's doing 11.25 megabits per second, which is our total capacity, divided by the capacity of the space required by an individual channel. But we can't do that because the units are different, so he's broken out those units for us, times 10 to the 6th, divided by 64, times 10 to the 3rd. And that gives us a number and the number I'm calculating that out gives us 175.7813 channels. But now what's significant about this number? When we get it to this point, we're saying that we can support, based on our calculations, we can support 175.7813 voice channels. But there's something about this number that isn't quite right. And Ryan says that we can't have 0.78 of a channel, and yeah, that's right. The question is asking us how many channels we can support, and Al says round down, and that's what we have to do. Because we can support, purely looking at data, we can support 175.78 channels. But like Ryan said, we can't have 0.78 of a channel. We either have a channel available or we don't. Because we're talking about voice, it has to be 64 kilobits of space. We don't have that, so like Al says, we have to round down. So we can actually only support 175 voice channels, 175 64 kilobit per second channels. Plus change, right, because we rounded down, so there's a little bit more space, but that doesn't matter to us because of the situation or the context that we're using this in. We have to have 64 kilobits per second channels. We can't have any smaller, we can't have any bigger. And so we can only support up to 175 channels with a little bit of extra space, which we might be able to use, but that's beyond the scope of the question. We don't care. Our answer is that we can support 175 of these channels. And so that's absolutely correct. And so through all the roundabout math, that is our answer for part A, is that we support 175 64 kilobit channels. But then if we look at part B, and again, this is less math, I promise. The A was the hard part. Part B is asking us, if the Earth station sent data rather than digital speech, so if we sent data instead of voice, what is the transmission rate? So basically it's saying, voice, there are certain rules to when we transmit voice. We have to transmit a certain range. We have to include a certain amount of data for voice to get over. But imagine if we were just sending digital data. So there's no rules. We're just sending a constant stream of data, 10, 10, 1110. We don't have any rules about how much space we need. We don't have to include certain frequencies to make sure everything gets included. If we're just sending data, what's our transmission rate? So if we don't have to worry about splitting it down into these voice channels, if we don't care about 64 kilobits per second channels, what is our transmission rate based on the calculations we did for part A? So again, forget about the channels, we don't care about that. We're just sending a stream of ones and zeros. How quickly can we send those ones and zeros if we don't have to split the channel at all? And we already did the hard work in A, so this doesn't require too much more math, thankfully. And Ryan says 11.25 megabits per second. That's right. Because look at this previous step. We calculated that each station can support up to 11.25 megabits per second just of raw data. And so that's what it's asking us. If we don't have to care about these subchannels, then this is what our transmission rate is. It's 11.25 megabits per second per station. And the important part there is to note that it's per station. Because that's not the total system. That's just saying per station. Because we have multiple stations in the system. And the question is specifically asking the data rate per station. And so for part C, and this is a little bit more math, but it's not nearly as bad, what is the efficiency of the TDMA system when we have, so let me write this out, part C, efficiency equals message bits sent divided by maximum number of possible bits. And so I'm going to let you guys sort of puzzle through this one a bit, but let's look at the first part here where we have message bits sent. So again, this is looking at a total system view because it's asking for the efficiency of the whole TDMA system. And so that system includes multiple base stations. How many message bits are actually sent in this system? And how can we figure that out? So again, this is looking at a system view, whereas before we were looking at an individual station view. So if we're trying to find the message bits sent in the system. So given the calculations we did, how can we figure out how many message bits are sent across the full system? You can either give the numeric answer or how you would calculate it. I'll accept either one. And Ryan says 5 times system capacity. Because we calculate, and that's right, because we calculated that each station can support 11.25 megabits per second of transmission. And we were told originally, I know it was a while ago, we were originally told that we have 5 of these stations working. So that means we have efficiency equals 5, which is our number, or number of stations. I'll just write it out. We have our number of stations, which is 5, times their individual data rates, which is 11.25. Now, the other part of the question to calculate the efficiency is the maximum number of possible bits that we could have sent. And so, how would we know the maximum number of possible bits that we could have sent? Because we figured out right here the number of message bits that were sent in reality, because each station supports 11.25. We have 5 of the stations. But what is our maximum number of possible bits? Something in our variables here must have told us what the maximum number of bits we could have sent is. So Al says number of channels times station capacity. What do you mean by channels there? Oh, I see what you're saying. Disregard the channels for now. We don't need to worry about the channels anymore because we're not strictly talking about voice. Again, we're just talking about bits. So we don't need to worry about the number of channels. That was only for part A because we're not talking about voice. We're still assuming that we're talking in a purely data-driven environment. But that's a good guess because we haven't talked about those channels in a while. But again, that was strictly for voice. We don't need to worry about sub-channels or number of channels. But you're on the right track. And Ryan noticed the bit rate. And that bit rate, the original bit rate we were given is 60 megabits per second. Because we were told that our bursts are transmitting at 30 megabaud using QPSK. And given those two variables, taking those alone, QPSK at 30 megabaud is telling us that we can push up to 60 megabits per second. And so that would be optimally, just given these two requirements, QPSK at 30 megabaud, we should be able to do 60 megabits per second. There's nothing stopping us from doing that except for the realities of the system. So here we have 60 megabits per second. And so that's the best we could possibly do based on our requirements is 60 megabits per second. But in reality, we're doing 11.25 at each station with 5 stations. And so that tells us we have 56.25 out of a possible 60. And I'll leave it like this, right? Because this is actually what it should be. 11.25 is already in megabits per second, so we don't want million over here to confuse us. So, but this is a ratio that we're looking at. We're broadcasting 11.25 from each station, and we have 5 of them. And so that means our in practical transmission, or our real transmission rate, is 56.25. But our numbers were telling us we could do up to 60 megabits per second. That, based on our variables given at the beginning, our maximum capacity was 60 megabits per second. And so our efficiency is the ratio of the two. It's how well we're doing in real life compared to our theoretical maximum. So if we do the division there and get our ratio, we have 0.9375 or 93.75% efficiency, which isn't bad, right? We're 93% efficient, almost 94% efficient. So we're being pretty efficient. And the only way we could change that number is if we reduced, for example, the amount of preamble time or our guard time, right? If each station was transmitting more data, then we would have a higher efficiency. But based on the numbers and the math that we calculated, that's the efficiency we're looking at. And so that's what we're looking at for 16.7. Again, up front, A is the hard part because we have to put together, basically, again, it's piecing together the information that we have to get an answer. And then part B and C are just analysis off of part A. And so the only other question that was mentioned at the beginning, and I know we're going a little bit long, please don't feel like you have to stick around. I just wanted to make up for some of the lost time from the first question. But 12.2 was the only other really math problem. Does anybody want to go over that one? Or it's mostly statistics, so I don't know how recently you took statistics, but I know statistics doesn't especially stick in my head very well. But the only reason I'm focusing on these 3 problems are that they're kind of the math problems from this homework. The rest of them are basically book reading and definitions. So I wanted to focus on the math ones because those are generally the trickier ones, or the ones that you're less able to just slam your head up against and find out by reading. But if anybody wants to see 12.2, let me know and we'll get over it. And then we'll wrap it up after that. But again, there will be another meeting on Sunday. So if either the activity or some of the book questions prove to be too tricky, we can go over them then. But I up front, I just like to get rid of the math because those tend to be the most frequently asked questions, or the math questions. I don't tend to have too much issue with the book definitions because they're typically there. They're just hidden and they take time. Ryan says statistics and I aren't friends, and I'll take that as a cue to go forward. But yes, I would agree that I appreciate the science of statistics, but it was not especially agreeable to me either. So for 12.2, I did about as much statistics as I needed for the program, and then I called it a day. Okay, so 12.2. We're consider a Bluetooth scatter net of 2 piconets. So 2 piconets. And those are basically 2 Bluetooth networks, to put into plainer terms. So we have 2 piconets. What is the probability of a collision between packets of the 2 piconets? Assume they're not using CSMA, so it's just randomly spitting it out there. They're not doing any additional verification. Remember that a successful transmission requires a successful polling message to be sent, and then a successful message sent from the slave to the master. Assume there are 80 possible frequencies. All piconets constantly have packets that are trying to send, and they are not using CSMA. So we have 80 possible frequencies, and again, that's how Bluetooth works. We have 80 possible frequencies to choose from, and based on Bluetooth, it hops between the frequencies and tries to send data. And so, imagine that we have 2 packets broadcast, or 2 devices broadcasting at once. We have 80 different possibilities where they could be broadcast. So think of it like 80 different roads, right? Or 80 different pipes. What are the odds that one of the... So we send 2 packets out at once, right? We try to transmit 2 at a time. What are the odds that there's a collision there, or that they're both using the same frequency when they broadcast? So again, there's 80 frequencies for them to choose from. What's the probability that they're both using the same one? And again, I'm using things like probability, which are statistics terms. Or I think the other way you can phrase this in statistics are, what are the number of ways that they could both be on the same network or same frequency? I don't need to see a decimal form. I'm looking for a fraction. I don't need to see big sign P or 1 minus equals. Hey Ryan, you're not so bad at statistics after all. So there's a 1 in 80 chance that they collide, right? Because if each of the 2 packets, so there's 2 packets, packet A and packet B. And packet A has 80 different frequencies to choose from. So it can choose from any of the 80. Packet B can also choose from any of the same 80. In order for them to collide, they would both have to have chosen the same frequency. So there's a 1 out of 80 chance that they both pick the same frequency. Because they would have to pick 1 of the 80 frequencies. So again, say we have frequencies numbered 1 through 80. They would both have to pick frequency 1. for that to happen. But in the other sense, what we're looking at is that if there's a 1 in 80 chance of them colliding, there's a 79 out of 80 chance of them not colliding. Right? Because one of them, if picking the same one causes a collision, there's 79 options where they don't collide. Because each of them could pick, if one of them picks one frequency, the other one has 79 choices of not colliding. I guess the easier way to think about it is this. It doesn't matter what frequency packet A goes out on, right? Packet A could be any of the possible choices. It doesn't matter. What matters is what packet B chooses. Because packet B, one of the 80 choices is the one that packet A chose. 79 of the 80 choices are not the one that packet A chose. And so our collision, 1 out of chain of colliding. And so those are the initial odds that we're looking at. But the important thing to note is that, like the book says, is that for successful communication to occur, we need to have an initial polling message and then a successful message. So for communication, we need a polling message and a message. So that means we need two packets for a successful communication. And so, and again, we're going back to statistics here. This is what we looked at. These are the odds, excuse me. These are the odds of an individual packet, or two packets having this problem, right? But now we have to do this twice. We have packet A, we have packet B, and then we have to do this whole relationship again. Because this is the first message, and let's write this down here. So that's our polling message, but then we also have our message. So polling message, and then our communication message. And so we're basically repeating these odds twice. And so statistically, how do we handle this? We're having the same communication happen twice. So we have a 180 chance of colliding, and then we have another 180 chance of colliding. So these are two linked events. Or actually, in statistics terms, they're two independent events, because one doesn't affect the other. But again, this is going into statistics a little too deep. So what's the relationship? How do we calculate the total probability of having something happen twice? We have the odds of the thing happening once, and then we have the odds of the thing happening again. How do we relate those two? And I can only hope you've had statistics at this point, because otherwise this will be unclear at best. I believe it's a prereq for this class, but we all know how prereqs tend to be flexible. Al says you haven't, and there's always a couple. That's why this will be, I mean, it's not hard statistics by any means, but it is. Ryan says you don't just add them, do you? And that's so close. But you actually multiply them. And that is the mistake that you can make, is that whether you have to add or multiply events. But because they're And again, I am not a statistics professor, and I don't like statistics any more than anybody else, I'm sure. But we actually have to multiply them. So we have the probability of success, right? Which is, and again, I'm going to do the probability of success. So we have 79 divided by 80, that it goes perfectly. And then again, we have a 79 divided by 80 chance. And we have to multiply them because it's statistics and they're related events that follow in precedence. And so the easiest way for me to illustrate that, I suppose, for those of you who haven't had statistics, is imagine you're flipping, oh God, I've got to be very sure I've got to be careful that I get this right. Give me 1 second to make sure I have this right before I shoot my mouth off. Okay. Imagine that you're flipping 2 coins, or you're flipping a coin twice, right? And so when you're flipping a coin, you have a choice of heads or tails. Those are your 2 choices when you're flipping a standard coin. And so you're flipping a coin twice, so we have 2 flips, heads or tails, heads or tails. And I'm asking you what the probability is that you get heads on both flips. And so if we map out the number of possibilities, so the number of what outcomes are possible, right? If we flip a coin twice, what outcomes are possible? We can get double heads, we can get double tails, we can get heads and tails, or we can get tails and heads, right? And those last 2 are significantly different. They don't look different because it's the same thing, but the order matters. And so you'll notice that the odds that you get heads are 1 out of 4, or 0.25% or 0.25. So double heads equals 0.25. Each of these probabilities is equally likely at a quarter. But the original probability of getting heads per coin is 1 out of 2 equals 0.5. And so because we have one event happening after another and order matters, I think that makes it, because we have one event happening directly after another and we're doing a comparison of both, we have to multiply together, because 0.5 times 0.5 equals 0.25. That's the absolute, like, bare basics statistical breakdown I can give of why this works. It's not directly relatable, but that explains why you have to multiply them at least, and hopefully the coin example comes through. Because we're comparing 2 events that are unrelated, but the precedence matters. The first one has to succeed in order for the results of the second one to matter for us. We have to multiply them together. And again, it's been a while since I took statistics too, so I could not necessarily explain to you why that is the case, but you will take that in statistics and you will see the relationship there. Anyway, back to the problem at hand. So this is the probability of success. Why can't I spell success? There's no extra S in there. I knew something was wrong. The probability of success is 79 out of 80 times 79 out of 80. Because remember, this is just looking at the odds that they don't collide, which we calculated here. They have a 79 out of 80 chance of not colliding. And so that number, which is, you could also square it, that works too, 79 divided by 80 squared, is equal to 0.975156. And again, I'll write it out a little bit longer than it needs to be. That's the probability of success, saying that the message goes through without any problems. But we're not looking for the probability of success. We're looking for the probability of collision or a failure to communicate. And so The easiest way to look at this, and again, let me just check my math to make sure there might be an easier way I can explain this. Basically, what we're looking at here is there's only two outcomes. There's only two possible outcomes. Either the message succeeds or the message fails. There's no other in between. And so what we do in statistics, if we're trying to look for the probability of something not to happen, we do 1 minus probability of success equals probability of failure. Because there's only two choices. You either succeed or you fail. So in this case, with the coin example, the probability of not getting double heads is 1 minus the probability of double heads, which is 0.25, so 0.75. 3 of your 4 choices are not double heads. Your probability of getting not heads is 75%. And so in this case, we're doing the same thing. You can either succeed or you fail. If you take away the chances of you succeeding from 1, right, the event happens, you end up with the probability of failure. And so in this case, we do the subtraction. We do 1, it's getting dark in here, I have to, 1 minus second answer gives us our probability of failure, and I'm running out of space here. 1 minus 0.975156 equals our probability of failure, which is 0.0248. And so, in other words, our probability that the message fails is 2.48%. Let me write that out, 2.48%. Or 0.0248. You can either write it in percent or decimal, it doesn't really matter. I like percents for probability because that's typically how we think of things, right? We think of something as having a 2% chance of succeeding or a 75% chance of succeeding. I just tend to like numbers in that sort of system as opposed to a decimal representation. But that's basically what we're looking at for this problem. And again, if you haven't taken statistics, hopefully this explanation was at least enough for it to make some degree of sense to you. Oh, where I lost it. Yeah, it helped. Good. Yeah, and that, again, that's fairly basic probability, but if you haven't ever seen it before, it can be tricky to wrap your head around it first. So again, we are over time now, but that's largely my fault. So thank you all for sticking with me. That was 3 of the math problems from the homework, basically the math problems from this homework. The rest are fairly definition-based, or should be you should be able to find it in the lecture notes or the reading. But again, there will be another session on Sunday. I saw the discussion board for the final practice was now available, so be sure to participate in that now that you've had some time to look over it on your own. Now you can start comparing notes and prepare for that. Don't forget about the activity and the extra credit if you want to do that. Those are both available, but also get ready for the final. Again, reviewing everything we've covered, reviewing the practice final will be hugely helpful, so make sure you do take the time to go over that and talk with everybody about it. I may schedule an additional study session sometime early next week, so that'll be dedicated purely to going over the final practice. I need to wait and see if we get a lot of discussion done in the discussion boards. We won't need that additional session, but I think it might be nice for some people to have a little bit extra time next week to go over just any questions, any lingering questions that they have before we tackle the final. I will make a post. I'll make an announcement about that when I make a decision. So I imagine we'll have something. I just don't know how long I'm going to do it or what day I'm going to do it on, but I imagine we'll have something. So I will see everybody then, and good luck with studying, and I will see you Sunday, if not next week. All right, thanks everybody.